Okay, so we are doing chapter 7 today. This is rotational motion. Okay, so now before I get into the slides, let me do something that'll help you understand the chapter. Okay, so what this chapter is about is the following. We'll be using some ideas from something called uniform circular motion. Okay, so what this means is the following. So this is a circular road, and you're going at constant speed on this road. You're driving at constant speed. And that's where this expression comes from. So uniform meaning your speed is uniform, and you're going on a circular path. Okay. So you guys have heard of the term velocity. Okay. Velocity is a vector. It has magnitude plus direction. Okay. So for instance, the velocity of this guy is his speed plus the direction in which you're going. Okay. Now as you're going around in the circle, your speed is not changing, and that's what we mean by uniform circular motion. Yeah.
Velocity is a vector. It's what was it?
Magnitude and direction.
Okay.
All right, so my question to you is the following. Okay. As you're driving in this circular road at constant speed, is your velocity changing? Okay.
It does, because as you go around, the centrifugal force causes you to go a little faster each time.
Okay, what is changing about the velocity? The direction is changing. Yes, your velocity is changing. Even though your speed is not changing, even though the magnitude is not changing, this is not changing, the direction is changing. All right, so this is important. Let's make sure we understand it. And so when velocity changes, that means you're accelerating. And if you want to accelerate, Mr. Newton tells us that you need a force to act on you. Okay? So if you want a non-zero acceleration, you need a force to act on you. Okay. All right, so in this case, so this is the velocity. It turns out that you're accelerating, and your acceleration at every instant is pointing towards the center of the circle. And it is called a centripetal acceleration. A for acceleration, the subscript C for centripetal acceleration. So you have centripetal acceleration. Okay. And your acceleration is equal to v squared by r. R is the radius of the circle, and v is your speed. All right, so did we all understand that? Okay. So when you're going in a circle, even though your speed is not changing, the direction of the velocity is changing, and so you're accelerating. Okay. And the magnitude of your acceleration is v squared by r. So the faster you're going, if you double your speed, your acceleration quadruples. If you're going in a circle half as big, if the radius is half, your acceleration doubles. Okay? It gets harder and harder. It's harder to go in a smaller circle at the same speed. Okay. All right, so let me give you a couple of examples of this. Okay. And we'll be using these ideas throughout the chapter. Okay. So let's make sure we understand this. Okay. So for instance, here's the sun, and here's the earth, going around the sun. Okay, the Earth goes at 30 kilometers a second. The speed of the Earth around the sun is 30 kilometers a second. That's about 20 miles a second. And of course, the speed is not changing. The Earth is going in a circular path. So is the Earth accelerating? Is the Earth accelerating? The speed is not changing. This is just like that. What is changing? The direction of the Earth's velocity is changing. You see, here's the velocity here, the direction is changing. So it is accelerating. Okay. So here's the velocity vector. The Earth is accelerating towards the center. The centripetal acceleration is the speed squared divided by the radius of the orbit. And this is about 100 million miles. Okay. So if you're accelerating, then there must be a force acting on the Earth. What is that force? The sun's gravity. That's what's making the Earth go around the sun. Okay? So the centripetal force is being provided by the force of gravity. Okay? The same thing is happening here on Earth. Here's Earth. Here's the International Space Station, which is about 250 miles above the surface of the Earth. This thing is going a little slower. It's going at about 8 kilometers a second. 5 miles a second. Okay? And again, it's going at constant speed, but the velocity vector, the direction of the velocity is changing. Okay? It has a centripetal acceleration. You need a force to make it go around. What is the force? I'm sorry?
Centripetal force?
It's the force of gravity. Earth's gravity is what's making the space station go around. Okay? So you need the centripetal force, and oftentimes we'll be looking at where the centripetal force comes from. Okay? So anytime an object goes in a circle, you need a force that is pointing toward the center of the circle to make it go in a circle. Okay? I'll give you one more example. So let's tie a ball to a string. Okay? Let's whirl the ball around in a circle. So, and now you know that the ball, when it's going in a circle, is it accelerating? Yes, it is. Again, because again, you need a centripetal force. Okay. The centripetal force is equal to mass times the acceleration, which is mass times v squared by r. What is providing the centripetal force in this case? Yep, the tension in the string, you're pulling on it. Okay? All right, so now let's, so here's the string. Okay, now let's imagine the following. What happens if the string snaps? So I'm whirling this ball in a horizontal circle. The ball is tied to the string.
There's no longer tension from the strings.
Yeah.
The velocity's gonna take over.
And what will happen?
It's gonna fly away.
Yeah, it'll just go straight. Soon as the string breaks, it goes straight. So now let me ask you something a little more radical. Okay, so let's say, so this is the sun. Here's the Earth going around the sun. Let's say after class you go home, flip a switch and make the sun vanish.
Earth will just fly off into space.
Very good. Okay, the Earth will fly off straight in space because there's no more gravitational force acting on it. Okay. Now this is a long story, I won't get into it. Will the Earth fly off immediately? In the case of the string, when the string snaps, this flies off straight immediately. In the case of the Earth, do you guys know how long it takes for light to get from Earth, from the sun to Earth?
10,000 years or something like that.
No. 8 minutes. Yep. Okay. So this distance is about 92 million miles, and it takes light 92 million, 8 minutes to travel that distance. Okay, so actually the Earth will fly off 8 minutes later. Okay, so anyway, so here's what I want you to remember, because we're going to use this. If something is going around in a circle at constant speed, the velocity, the direction of the velocity vector is changing, and so it's accelerating. The acceleration is called centripetal acceleration because that acceleration is pointing towards the center. And to make anything accelerate, you need a force. And we'll see where the force is coming from. Okay? So that's what the entire chapter is dependent on. All right, so let's get into the slides. Okay, so now you guys understand this ride. Okay, so in this ride, this is rotating. All these people are going in a circle. Okay, and so the centripetal acceleration is v squared by r, and v can be, again, you don't need to remember all these formulas. R times omega. R is the radius of your circle. Omega is your angular speed. Angular speed is your rotational speed. You see, everybody has the same angular speed because this thing is rotating at the same speed. Okay, so this turns out to be r squared omega squared divided by r times omega squared. The centripetal acceleration is that, okay, r omega squared. So bigger your r, greater your acceleration, more exciting your ride. So even they all paid the same money, this guy's having the most fun. All right, so these people got gypped. All right, so they're all going in a circle. You need a centripetal force, and this cable is what is providing the centripetal force. That cable had better not break, because the cable breaks, you go flying straight. Okay? So in uniform circular motion, the acceleration is directed toward the center of the circle. We call it the centripetal acceleration, okay? For obvious reason, because the acceleration is pointing towards the center, okay? Now here's the reason we're talking about this. Here's this lady walking, and here's how walking happens. Here's what you do when you walk. So you plant your foot, and then your center of mass pivots around it. It's like a pendulum, inverted pendulum. Your center of mass is going in a circle. Okay? So to make anything go in a circle, what is it that you need? You need a force towards the center. You need a centripetal force. And we'll look at where the forces come from. Okay? So we'll see that. And here's where the forces are coming from. So here's the center of mass. So here's the center of mass at the midpoint. Here's the weight of the person. That's the lady. The weight of the lady. And you see there's a normal force on the foot pointing upwards. There is the normal force. That's the push of the ground on her foot. That's the normal force. Okay, so the centripetal force, you need a force in toward the center. So the centripetal force is the weight of the lady. Weight is mass times gravity, m times g, minus the normal force, and that is equal to the centripetal force. Okay, r is the length of the lady's leg, v is the speed at which she's walking, m is her mass, and so the weight minus the normal force is equal to this. All right, so listen to this carefully. So let's say you want to walk faster and faster. You want to make this guy bigger and bigger. Does your weight change? So if you want to make this bigger, this has to be bigger. This is equal to that. This doesn't change. So the only way you can walk faster is make this smaller.
What's the N represent?
That's the force with which the ground is pushing you. That's the normal force. That's the force on your leg. So as you're walking faster, your foot is hitting the ground lighter. What is the best you can do here?
Running.
This becomes zero. That's the best that can happen. You can't get to that limit. If that could become zero, then you could walk on water. Right? So the best that can happen is this can be zero. So if let's put that zero, and then you can calculate your speed. That's your maximum walking speed. Okay? So that's the maximum walking speed. So if this height is about 0.7 meter, which is a little over 2 feet, that's the average foot length, it turns out that your maximum walking speed is given by this, V max squared divided by R, mass cancels, V max is G times R. So your maximum walking speed is the acceleration due to gravity times the length of your leg, square root of that. And if you put in average numbers, this comes out to be about 6 miles per hour. So if your foot is 0.7 meters long, the maximum walking speed is that. All right, giraffes have longer legs. They can walk faster. Okay. It turns out that mice have such small legs that their maximum walking speed is so small that they hardly ever walk. Mice always run. Okay. So your maximum walking speed is about 6 miles an hour. But it turns out that about 4 miles an hour, do you guys understand? This is applicable everywhere. About 4 miles an hour, it turns out that running is more energy efficient about 4 miles an hour. So you don't walk at 5 miles an hour. You run. And in fact,
Try to walk at that speed.
what's that?
It's awkward to try to walk at that speed.
Yeah.
Runners like it.
Yeah. So here's the amazing part. Okay, you get on a treadmill. This is absolutely amazing. Your body knows all this stuff. Okay, you get on the treadmill and you start making the treadmill go faster. Your body automatically switches to running at the very speed it's more efficient for your body to run. All right, this supercomputer that you walk around with, it's very smart. All right.
Well, isn't it just trying to prevent you from tripping and falling?
No, it's all about energy efficiency. And in walking at high speeds, it's like our friend here pointed out, walking is unstable as well. Okay? All right. So again, we use the idea of circular motion. Okay. So the maximum speed at which you can pivot or turn a corner is determined. Okay. So this is also talking about turning, but anyway, your maximum walking speed is determined by your center of gravity moving in a circular arc as your body pivots over your front foot. Okay. All right. So here's you see rotational motion. You do a lot of rotational motion when you're playing sports. So for instance, when you're playing tennis, you see your arm is rotating about your elbow. And so you have to apply torques. Okay. And in tennis, you're holding a racket, which is long, and then you're hitting that ball and stuff like that. You stress your tendons quite a bit. Okay. Tennis elbow is when you harm your tendons there. Okay. And when you're throwing a baseball, see again your arm is going in a circle. Okay. So stresses of this exertion can lead to injury such as tennis elbow. Okay? All right. So here we go. Again, we're going to go around in a circle. The green vectors are velocity vectors. Okay? And you see the speed is not changing. The length of the vector is not changing. But the direction of the vector is changing. And so you have a centripetal acceleration. At every point, the acceleration is pointing toward the center of the circle. And that's why it's called a centripetal acceleration. Okay? And anytime you have an acceleration, Mr. Newton tells us there needs to be a force acting on you. Okay? So if it's a centripetal acceleration, we naturally call it a centripetal force, and so on. Okay, so anytime anything is going in a circle, there must be a force acting on it. Okay? So velocity is a vector that has both speed and direction of motion. Although the speed may be constant, the speed is constant, an object moving in uniform circular motion has a constantly changing direction, and so it's accelerating. And there is the acceleration. There is the magnitude of the acceleration. Your speed square divided by the radius of the circle. The time it takes to go around in a circle is the circumference of the circle divided by your speed. That's the time to complete one circle. Okay. All right, so here's the quasar ride, and so in this quasar ride, so you initially start off when it's at rest, these buckets are pointing down like that, you get in, and then as it goes faster and faster, you see the bucket has become horizontal. Yeah. And it turns out that the centripetal acceleration is as large as 20 meters per second square. So the centripetal acceleration is 20 meters per second square. That is, G is 10 meters per second square. G is 9.8 meters per second square, roughly 10 meters per second square. So this centripetal acceleration of 20 meters per second square is 2G. That means this seat is pushing you inward with a force twice your body weight. Okay? So this seat is pushing you up with a force equal to your body weight, and in the horizontal direction at twice your body weight. So that's what makes these kinds of rides exciting. Yeah. All right, let's make sure we understand this stuff. Okay, so they ask you for the period of motion, and we'll also see the centripetal acceleration. Okay, so this and centripetal acceleration is, okay, so I'll write down, let me write down the formulas. So centripetal acceleration is v squared by r, and the period, which is the time it takes to go around the circle, is 2 pi r divided by v. Okay, so we're going to rank these guys. Okay, so let's do the centripetal acceleration first. Okay, for this guy, it's v squared by r. For this guy, the speed is doubled, so 2v squared by r, which is 4v squared by r. So for this guy, the speed is doubled and the size of the circle is the same. His centripetal acceleration is 4 times this guy. You need a force 4 times as great. To go in this circle, it's 4 times as hard. Okay, that's what that means. For this guy, the centripetal acceleration is v squared over 2r, so 1/2 times v squared over r. So you're going at the same speed as this, and the circle is twice as big. This is easy. It takes half as much effort as to go in this circle. Okay? So that's what those things mean. Okay. How about this guy? The centripetal acceleration is 2v squared divided by 2r. So that is 2v squared over r. Well, in this case, the speed doubled and the radius doubled as well. It turns out that it's twice as hard to go in this circle as that. So the greatest centripetal acceleration is for this guy. It is hardest to make this circle. Okay? You double your speed, the acceleration quadruples. Okay? All right, now let's look at the time. The time is 2 pi r over v. For this guy, it's 2 pi r over 2v. Okay, so it takes only half the time. For this circle, it only takes half the time as to make this circle. And that makes sense. You're going twice the speed, and so it only takes half the time. Okay. For the third guy, 2 pi into 2r divided by v. Your speed is the same. The circle is twice as big, so it takes twice the time. 2 pi r over v. And for the fourth guy, 2 pi 2r over 2v. It takes the same time. It takes the same time to go around this circle as for this circle. Your speed doubled, but the size of the circle doubled as well. Yeah. All right, make sure you understand that. There's questions on the test on that. So I'm giving away. All right, so again, the punchline of this chapter is, even though you're going at constant speed around a circle, the direction of the velocity vector is changing, you're accelerating, and so there needs to be a force, okay, acting towards the center. The acceleration is called the centripetal acceleration, and the force is called the centripetal force. So you need a centripetal force to give an object centripetal acceleration. Okay? All right, so this piece of information will be useful when you go to the forest next time. So here's Tarzan swinging off a vine. And you can see that his center of mass is going in a circle. Okay? Now, in reality, he's speeding up. He's going at maximum speed here, and then slow down. He's slowing down. But we'll say that his speed is constant in this portion. He's going in a circle. His centripetal acceleration is in that direction. You need a force in that direction to make him go in this circle. Well, where's that force coming from? Okay, here his weight is acting this way. So something must provide a force in that direction, and that's the tension in this vine. Okay? So the tension minus W is mv squared by r. Tension minus his weight equal to mv squared by r. R is the radius of the circle. Now this doesn't change, so the faster you're swinging, the greater the tension. The faster you're swinging, the stronger the vine better be. You don't want to grab onto a thin line, okay? But your supercomputer automatically tells you that. Okay? In fact, it turns out that at this point, the tension is the greatest. At this point, the tension is not as great, any other point. So if the vine were to break, it would break right when you were at the bottom. Okay? So here's a competition, okay, where this guy swings this hammer around, and what wins? You know, the guy who throws this the furthest. So let's go back to this. We'll go back to that string example. So here's the hammer being swung around, okay? So what he does is he swings around, he goes faster and faster. As he's spinning faster and faster, the centripetal acceleration is increasing. He's having to pull harder and harder. Okay? And so it gets harder and harder to hold on to it. Okay? And if he's throwing in this direction, he lets go at this point, and he's spinning as fast as possible, and then at this time he lets go, and so since this tension is not there, this hammer will fly. Okay? And that's the idea of the competition. All right, so you swing around. At the last minute, there's the force you're applying, and you can't apply any greater force. Otherwise, your arms will come off from your shoulders. Okay? And you're trying to achieve the greatest velocity before you throw it. You guys understanding this? All right, so here, so what we'll look at is now a turning corner. So you're at a four-way stop, let's say, and you want to make a turn. So you see you're going in a circular track, along a circular arc. When you're going along a circular arc, you need a centripetal force in that direction. Okay, so let's see what's happening. So here's the circular road, you're making this turn, okay? And the car is moving in this direction. What you need is a force in this direction, okay? Centripetal force. And that is coming from a static friction force, because the car is not moving in this direction, and that's why it's a static friction force. And that's from the stickiness of the tires on the road. So if the tires were not sticky, you couldn't have this force, and you couldn't make this turn. So for instance, if the roads were totally icy, you can turn your steering wheel all you want. Your car will just go straight. Okay? So if your tires were not sticky, if you had no friction, there's no way you're making a turn. You can turn your wheel all you want.
That's why you're not supposed to touch it when you hit black ice.
What's that?
That's why you let go of the wheel when you hit black ice.
Yep.
You're gonna make it worse.
Yeah. Well, you can't. I mean, you're just going to go straight. Yep. You're going to panic. Your brain is going to get, your supercomputer is going to get confused because you're turning the wheel, and the car is not responding, and you freak out. All right. So the static friction force is providing the centripetal force. Now you saw that the static friction force has a maximum value, and that is mu s, the stickiness of your tire. Okay? So racing tires are stickier. You can make a faster turn. And times the normal force, so here's the weight of the car, and there's the normal force. The normal force is equal to the weight. Okay? So it's equal to mg, and that's providing you the centripetal force. So that is the maximum speed at which you can make a turn. So mu s, the stickier your tires, the faster you can make a turn. For a given stickiness, okay, smaller the radius of the turn. Okay, if this gets too small, this will get larger than that. You can't make that turn. Okay? And so if your tires are not sticky enough, there's a minimum radius or the maximum speed at which you can make that turn. Okay. Here's what happens. And so the stickiness, because of the stickiness, you're leaving some rubber on the road. So every time you make a turn on level road, you leave rubber on the road. And this costs the country billions of dollars. Really, for real. Yeah. How do you fix that? Yeah, go ahead.
Is rubber left on the surface of the road beneficial to other drivers in the sense that it might create more of a sticky and create a more sticky texture and more friction, or does it somehow smooth the surface of the road, making it have less friction and more slippery and more of a safety hazard?
No, it makes it sticky, but then everybody's leaving rubber, and then you're having to replace your tires sooner.
Oh yeah, the tires are wearable items, but does it impact the road in a negative way?
No, it doesn't. But as a policymaker, what you want is to save the country money. Okay, so this is a real concern. How do you fix that? Yeah.
Make the turns not so tight.
Here you can't do anything, but in places where you can, what you do is you bank the road. Okay, so let's look at this. So now if you bank the road, okay, this is the normal force. The normal force is the force with which, so here's the car, it's banked, and the road pushing up on the car is perpendicular to the road. There's the normal force. Okay. This component of the normal force, so this component of the normal force is balancing the weight, and this component of the normal force is providing you the centripetal force. Okay? So if you go at the right speed, then this will provide the centripetal force. If you go faster than that, then you need a friction force, and you'll leave rubber on the road. If you go too slow, the friction force has to act that way because this is too much, and this you have to use, you leave some rubber. If you go too fast or too slow. Okay, if you go at the right speed, this component of the normal force provides a centripetal force. Okay, so on a banked road, the normal force has become larger, and it's at an angle, and it's providing the centripetal force. Okay, so here's the correct angle. So if the angle is banked, so if that is the bank angle, tangent of the bank angle, if you go at this speed, then you don't need any friction force. So that's why all the exits are banked. Okay, so and the speed marked at on the exits, that's this speed. So if you go at that speed on the exit, you don't need any friction. Even under black ice, you won't go off the road. Okay, you can leave your hand off the steering wheel. You go at that speed, and you won't go around the turn. All right.
So does it also technically change their center of gravity,
What?
making it easier to turn?
No, it's not changing the center of gravity. No. So all this is about is not having to use friction force. It's just the normal force providing you that. There's something very neat about this formula. Can you tell me that? Do you notice something? It's very neat. Okay, so let me put it another way. You've seen that speed marked on that exit, right?
Yes, 25 on or yeah, sorry, 25 on the curve or something, yeah.
Does it say what vehicle you're driving? The mass of the vehicle is not there. It's the same for a semi, for a car, for a motorbike, for anything. The mass cancels out. Every vehicle will not use any friction. A semi won't skid under icy conditions, neither would a car nor a SUV. Okay? So that's what the bank is about. So, I mean, making that bank it takes money, extra money. Why would you spend all that money? One, it's safe, but you're also saving money. Why are you saving money?
Less tire wear.
There you go. There you go.
And the more people that are on the road,
Yeah,
the less
see?
tire wear, the more you get income from the community and stuff. So.
All right.
Everybody's
So,
always going through tires so fast, nobody's gonna go anywhere.
yep. So everything is done for a good reason. Yeah. All right. You've all experienced this. When you make a turn, you lean into the turn. Okay. Without leaning into the turn, you couldn't make the turn. Okay. So you can't make a turn going straight up. And as you lean in, your tire wants to slip, and it's the static friction force that's providing the centripetal force. Okay. So the faster a cyclist goes around the turn, the more he has to lean. Understand that. The stickier the tires, the faster you can make a turn. So if you have very non-sticky tires, then it's harder to make a fast turn. Okay? So if you wanted to make a fast turn, what can you do to make tires stickier?
Heat it up.
Heat it up. Or if you have less air, more surface is in contact and you can make it stickier. Okay? So, all right, so just like in the case of the banked road, this is the lean angle, theta, okay? And so this is providing the centripetal force, okay? So this is the centripetal force. The centripetal force, the friction force is providing you the centripetal force, and the normal force is equal to the weight of the guy. So now when you lean, so here's the deal, and your body figures this out. The lean, so this force, these are the two forces that the ground exerts, the normal force and the friction force. And the sum of these forces is that force, and that has to pass right through the center of mass. Your body automatically calculates and leans at the right angle. Okay? So, so this is that. So tangent theta is this divided by that. Tan theta is the friction force divided by the normal force. Tan theta is v squared by gr. If that is the radius of the circle and that is the speed at which you're going, this is the angle you have to lean at. Okay? And you don't have to know any physics. Your body knows that. Okay? And through years of practice, you've learned that. Okay? When you're a kid first, of course, when you're first doing that, you don't know that, and you fall. Okay? And a few falls will teach you real good. So now the question is, what is the maximum angle you can lean at? Okay, the maximum angle you can lean at is mu s times this. That's the stickiness of the tires, and so the maximum angle is this divided by that. So that is that. So the maximum angle you can lean at depends on the stickiness of the tire, which determines the maximum speed you can go at or the minimum circle you can go around. Okay. All right, so this formula tells you the stickier your tire, the greater you can lean, and the faster you can go around the circle. Okay.
So that would be in motor, like,
Motocross?
yeah,
Mm.
when you lean, that means that it has to be stickier than anything else because they're almost touching the ground when they're going around the circles.
Mm-hmm. Well, it appears that they're touching the ground because their ankles are almost scraping the ground, but what it matters is the motorbike is like that, and your ankles are touching the ground. Okay, so it's the angle of the motorbike that matters. And you know they're almost riding on the edge because you slip and fall, your race is over. Yeah. You want to push the limits, but you also don't want to fall. Yeah. So maximum walking speed, we've already talked about this. So you plant your foot and your center of mass pivots around your foot. Your center of mass is going in a circle. You need a centripetal force in this direction, and that is coming from the weight minus the normal force. Okay. And your maximum speed is determined in the limit of the normal force going to 0. Okay. That can never happen, but that gives you the limit. Okay. In a walking gait, your body is in a circular motion as you pivot on your front foot. Okay. So there's your weight minus the normal force providing you the centripetal force. And that's equal to mv squared by r. So the maximum walking speed comes when n is 0. Okay? So the normal force becomes smaller as you walk faster. Okay? So as you're walking faster, this force is becoming smaller. Again, your foot on the ground is impacting at lower speeds. Okay? The maximum walking speed occurs in the limit n equal to 0. So n equal to 0 just means mg equal to mv squared by r. Okay. And your maximum walking speed doesn't depend on your mass. It doesn't depend on your weight. It just depends on the length of your foot, length of your legs. Okay. So it just depends on the length of your legs. Is set by r. The maximum possible walking speed is set by r, the length of your leg, and g. Okay, so if you want to walk faster, what can you do? You can wear stilts and you can walk faster. You know? So giraffes with very long legs can walk at high speeds. Animals such as mice with very short legs have such a low maximum walking speed that they rarely walk. They rarely use that gait. You know? For humans, the length is approximately 0.7 meters. So from here to the ground is 0.7 meters. And the walking speed is about 6 miles per hour. Yeah. You can walk this fast, though it becomes energetically unfavorable to walk at speeds above 4 miles per hour. So most people make a transition to a running gait at about 4 miles per hour. So let me show you a little graph. So you see, here's your speed. This is the energy used per kg per pound of your body. Kg is 2.2 pounds per meter run. So energy used per distance covered. And you see, below this speed, walking is favorable. And above that speed, running is more energy efficient per unit distance run. And so if we put you on a treadmill and start increasing the speed of the treadmill, you'll walk till this point, and then at that point, you automatically switch to running. That's how powerful your brain is. Okay? So if we were on a treadmill whose speed gradually increases, the point at which we spontaneously switch from walking to running coincides with the moment when it becomes more energy efficient to run than to walk. Yeah. You should try this. If you try it as homework. If you go to Planet Fitness or whatever. Okay. So the transition happens at about, yep.
I'm old, I don't run unless I'm chasing an ice cream truck.
Well, so there you go.
I'll have to summon one to my house then, so.
Use one of your kids, same experiment.
Right.
Well, kids' legs are different, so so their transition speed occurs at a different speed. It depends on the length of your leg. Yeah. Well, all you have to do is make sure that the truck is going faster than 4 miles an hour, and then you will know that you're running and not walking. All right, so walking versus running. When you run, so we saw that walking can be modeled as an inverted pendulum. In walking, you plant your foot and your center of mass is going in a circle over it. Okay? Running can be modeled as a spring mass system. So your tendons are springs that store energy. You guys remember how much energy does the tendon give back? 90%, very good. Okay. So in a running, so here's your central mass. When you plant your foot, your tendons compress. Okay. They store energy, and then they'll give that energy back. Okay. And so you use so your center of mass. So it's like this. When your center of mass is high, it has gravitational potential energy. When it goes lower, that gravitational potential energy is decreased. Okay, so your center of mass, it lost gravitational potential energy. That energy got stored in the spring, and then the spring gave it back and it pushed you back up. Okay. So here's a nice diagram. Here's the energy flow. Okay, so this is energy conservation. So here's your center of mass. You plant your foot, and look what happened. your tendons stretched. They stored that energy, the gravitational potential energy that you lost, and then the tendons go back to they gave back the energy, and your center of mass went up. So here your muscles don't have to work, or not as much. Okay? So you do this when running, hopping, walking, okay, and so on. So here is when you're climbing up a stair, for instance. Okay? So here your center of mass, you have to lift your center of mass up. Climbing upstairs, you have to spend money. You have to spend energy. Okay? So here you see your muscle contracted. It stretched the tendon, so your muscle did work, stored energy in the tendon, and then when you climbed up, this tendon energy was transferred to your center of mass. So when you're climbing uphill, you have to do work. What if you're walking downhill? All right.
Less work. Gravity work.
No, so here's gravity. You lost, the gravitational energy was lost, and you see that was stored in the tendons. But you don't want to climb up, so you have to dissipate this energy. You got to convert that to heat. And what that happens is it stretches the muscle, and the muscle dissipates it. Okay, so you want to get rid of your energy. Okay. All right. Running can be modeled at slow speeds. The pendulum-like mechanics of walking are efficient. At slow speed, walking is efficient. As speed increases, the up and down motion of your center of mass becomes too costly, energetically costly, and mechanically unstable. Okay? So you correctly said that walking is fast is uncomfortable. During running, tendons act like springs, storing energy when stretched and releasing it during recoil to help propel the body forward. Okay, and you guys remember kangaroos use that quite efficiently, and because of the long distances they cover, they have huge tendons and so on. Yep.
Okay, so when you talk about tendons storing energy,
Mhm.
in my mind, it goes to the Wakanda movies with like the suit. Every time the Black Panther, I don't watch it very much, but anytime the Black Panther would get hit, it would store the energy, and then the harder the impact, the more force he exuded from his suit. Somebody running, would it behoove them to step harder or impact the ground more, even though it puts more wear on your bones, but would it then create more energy to be stored in the tendon because of the amount of impact?
No, so the tendon stretching depends on that impact. You're just hurting your bones.
Okay.
Yeah. It's all the bending and the right techniques.
Because then my mind went to a gymnastics floor, which usually has a little bit of spring to the floor to, I guess, help with impact so it doesn't hurt the gymnast as much.
Yep.
But then I would thought that would affect their energy being stored in their tendon and the release, and therefore affecting their ability to get height or go further. So.
No. So, I mean, on a hard floor, a good technique, good landing technique will hurt you less than bad landing technique. And bad landing technique over time, even on the soft floor, hurts you. Soft floor is just buying you insurance. Okay. Storing energy is about making sure that the tendon stretch right. And if you stretch it too much, of course, you can tear tendons too.
Right.
Yeah. So, to stretch tendon, muscle must actively contract and generate force. So, when you're stretching the tendon, the muscle contracted, it did work, it cost it ATP, energy, to stretch the tendon. So, the work done by the muscle is stored in the tendons. Okay? To generate force, which consumes metabolic energy, you consume ATP. the work done by the muscle is stored to use strain energy in the tendon, okay? So it's like when you stretch a rubber band, you've done work to stretch a rubber band, and all the energy you spent got stored in the stretched rubber band, okay? Muscles dissipate energy stored in tendons through a process where the recoiling tendon stretches the muscle fiber. Okay, so when you are going downhill, the energy stored in the tendon had to be dissipated, turned into heat. You don't want to turn that into motion. Okay, and so what this did was when the tendons relaxed, it stretched the muscle. And then the stretched muscle will dissipate that energy. We have a very precise, intuitive perception of energy efficiency of a particular style of movement. So your body knows at a given speed what is more efficient. Is it walking or running? And it automatically chooses that. Okay, so I gave you the treadmill example. You can test this out. So, let's see, walking is more efficient. So this is the energy used per meter. That is per distance covered, unit distance covered. Okay? For most people, the transition from walking to running happens around 2 meters per second. That's 7 kilometers per hour, or about 4.5 miles per hour. Studies show that the energy cost per distance, and the way that they measure is they put you on a treadmill, and they have this mask on you, and they're measuring how much oxygen you're consuming. Okay? So oxygen consumption per meter of walking rises steeply about 2 meters. See, the energy consumption rises steeply for walking, about 2 meters. Running while consuming more energy per second becomes cheaper per meter as the speed greater than about 2 meters per second. Okay. Do you guys know what a centrifuge is? Anybody has? Okay. Have you used a centrifuge?
I have.
Okay. So you use it for work?
No, I had a friend who had one for, she runs a cat rescue, and she was spitting down blood to test for something, parasite or something, or bacteria or whatever. And we spun the blood down, and then we looked at it under a microscope and stuff. So.
Cool. All right, so what a centrifuge does is the following. So let's say, what's that?
It's the spinning machine.
It's a spinning machine. Okay, so here's what it does. So, you take a glass of water and put some clay, stir it all up, and then if you let it settle, it'll all settle eventually. Of course, the biggest particles will be at the bottom, and then the smaller particles, and so on. Okay, and so on. But this might take, if it's large particles, it'll settle in minutes. If it's smaller particle, it might take all day. Even smaller particles, it might take weeks. So if you have cells, red blood cells and all, they're small particles. If this was blood, the cells would settle, but it would take days or weeks. Okay, and that's too long. So you want to be able to speed it up. Okay. Now, the settling rate depends on the strength of gravity. Now, you can't ask the Earth to have stronger gravitational field. Okay? So if you could somehow increase effective gravity, then you can make it settle faster. And that's what this spinning does. Okay? So the settling speed, the terminal speed, depends on the particle density minus the liquid density. So if your particle's density was equal to the liquid density, you couldn't separate stuff. And it depends on the gravitational force, acceleration due to gravity. So a centrifuge, what it does is, well, you can't change this. Whatever you're separating is what you're separating. What you're doing is you're changing this guy. You're making this, you want to settle it 1,000,000 times faster, you just got to make this 1,000,000 times greater. And that's essentially what you do. So the effective gravity is V square divided by R. V is the speed at which you're spinning, and R is the radius. And you can make this 1,000,000 times faster, 1,000,000 times greater than G. And you can make it settle 1,000,000 times faster. Okay, so for microscopic particles such as cell components, the settling time even under ideal conditions may be days or weeks. So if you just took blood and put it in a cup and waited for it to settle, for stuff to settle, it'll take days and weeks. Okay? Even under ideal conditions, where nothing is shaking that and all that. In which diffusion and temperature variations cause some mixing. Temperature will cause some mixing, and then it'll take longer and longer. Okay. A particle's terminal speed, how fast it settles, is proportional to the difference in density as well as G. Okay, so a centrifuge, you're increasing G effectively. Okay, so again, the effective G is speed square divided by R. That is the centripetal acceleration. Okay, and so the densest particles will settle there, and then the next dense, then the next dense, and so on. Okay. Yep.
So for the forming of a particle out of a liquid.
It's rho.
Oh,
That is, it's a Greek letter,
okay.
rho. That's the symbol used for density.
So for when we are like for blood,
Mhm.
when that's in the centrifuge,
Mhm.
what would that look like with that?
So the particle, that would be, let's say it's a red blood cell, that would be the density of the red blood cell. Minus the and the liquid is, of course, plasma. Yeah. So you can Google the density differences. Yeah. All right, so ultracentrifuges spin at 75,000 RPMs, 100,000 RPMs, 120,000 RPMs. You can buy these centrifuges. Okay. Now, of course, here's the thing, you got to be careful. When it's spinning that fast, you got to balance the weight. If you have a test tube of 20 grams here, you'd better have a test tube of 20 grams. And if you have only one sample to spin, what do?
It's gonna explode, it's gonna.
Yeah, you put a dummy, just water there or what?
The other mix,
Yeah, yeah. So you have to have a balancing liquid. Okay. So these guys can spin very fast. Okay? And of course, this material has to be strong. You don't want stuff breaking. Stuff spinning at 75,000 RPM, so, You can test this out. You have a centrifuge. So you can test this out. You do a vertical spin like that, and your blood will collect in your arms, and your arms will get thicker. Hands will get thicker. You can do it.
That's how my husband gets the last bit of the ketchup out of the ketchup bottle. He spins it around until it goes to one end.
See, guys are not entirely stupid. All right. So.
It's so cute when they think they're clever.
So.
Oh man, it's rough.
We love our husbands.
Yep. Sometimes.